Hello, everyone. Good afternoon, and welcome to today's event of International Webinar come Online Students Presentation, a slice of the heavens rising above the pandemic, organized by the Postgraduate and Research Department of Physics of St. Xavier's College, Kolkata, in collaboration with the Xaverian Astronomical Society. In the splendid hours to be followed, be prepared with exuberance to witness the international webinar titled Extragalactic Radio Sources for Navigation, followed by the students' presentation. However, before we proceed, I would ask everyone present here to observe 1 minute of silence in the memory of late Dr. D.N. Bose, ex IIT Kharagpur faculty, who was currently a faculty in the Department of Physics of St. Xavier's, teaching the postgraduate course. Thank you. Now, I would invite Reverend Father Dr. Dominic Savio S.J., Principal of St. Xavier's College, Kolkata, to initiate the welcome address and give a resplendent start to today's event. Father, the platform is yours. Thank you.
Father, please switch on your audio.
Sorry. A very good evening to all of you. A warm welcome to our guest speaker for the webinar, Dr. Sayan Basu, esteemed faculty members and members of the administration, and all the participants for the webinar and our dear students. Currently, we are experiencing an unprecedented global crisis. The COVID-19 pandemic has brought the world to a standstill. However, this halt in our routine life must not necessarily cause a halt to learning. Knowledge is still accessible to all through the online medium. In keeping with this, the college postgraduate research department of physics, in collaboration with the Xaverian Astronomical Society, has organized an international webinar and students presentation, a slice of the heavens rising above the pandemic. This webinar presents an opportunity for physics and astronomy enthusiasts to access knowledge and engage in scientific discourse. The physics department is one of the oldest and prestigious departments of the college. The department was developed under the pioneering guidance of renowned Jesuits like Father Lafont, Father Westerton, Father Bonhomme, and others. The physics department of St. Xavier's has a renowned name in the field of scientific education in the state of West Bengal. Over the years, the department has grown and developed into its present structure with the UG and PG departments as well as research facilities. The department also manages the Father Eugene Lafont Observatory, which apart from serving as a standard laboratory for astrophysics students, is also used for observing astronomical phenomena by the faculty, college students, and students from rural schools as part of outreach initiatives. The Xaverian Astronomical Society was established in 2019 by students from the physics department of the college. It now has numerous members from various departments of the college. The vision of the society is to utilize the facilities of the observatory to further the Jesuit ethos of social justice and magis in the true spirit of Nihil Ultra. It also aims to help the college maintain and enhance its rich legacy of quality teaching and research. It intends to popularize physics and astronomy among the students from various backgrounds to help to produce men and women of scientific temper who value equity, justice, and scientific pursuit. To further the mission of the society to organize and conduct workshops, seminars, quizzes, and other events to strengthen the position of the observatory. The society had conducted an interactive astronomical workshop for rural students as a part of an outreach initiative just before the nationwide lockdown. I take this opportunity to welcome our principal speaker, Dr. Swayan Basu of the Department of Physics, University of Pretoria, and South African Radio Astronomy Observatory, our faculty members, the participants of the students' presentation, and all webinar participants on Zoom and YouTube. I hope this slice of the heavens benefits you in rising above the pandemic. May this season prove to be fruitful and engaging. I congratulate the organizing team for their efforts and wish them a successful event. Thank you. Wish you all the very best. May God bless you.
Thank you, Father, for kind words. Now, I would like to request the Secretary of the Xaverian Astronomical Society, Shashwat Saraf, to say a few words.
Am I audible now?
Yes, you are audible.
Thank you, Father, for your words of wisdom and your invaluable inspiration and guidance in our society's formation and continued activity. As founders of the society, Ankit Kumar Gupta, my assistant secretary, and I had envisioned that XAS would give students of all backgrounds valuable exposure to astronomy, expose one and all to the thrill of discoveries, and help develop the youth into leading scientists who value social justice and a scientific outlook. One of our foremost goals has been to motivate socially disadvantaged children to pursue science and higher education through specially arranged activities. We will be observing our first anniversary in the coming month, and I am pleased to say that within this year we have progressed towards our goals. In accordance with our aim to reach out to people of all backgrounds and motivate underprivileged youths, we had visited a government school in a village and conducted an interactive quiz with the children. Thereafter, we had also invited those young students to our college for an interactive model making workshop. We were very happy to see their excitement when we later took them to our observatory to give them a first hand experience of observation through an astronomical telescope. We hope to see much more from XAS in the forthcoming sessions. However, none of this would have been possible without the help and guidance of many people, including especially our Deputy President, Dr. Shibaji Banerjee, whom I would now like to invite to elaborate on the history of the observatory and the society.
Thank you very much, Shashwat, for your introduction. And thank you, Father, for being us today and always for your continual support that you have shown for keeping the spirit. Am I audible?
Yes, yes. Very
Yes,
much.
sir.
Very
Am I
much.
audible? Yeah. Yeah. Thank you, Father, for being with us today. And always for your continual support that you have shown for keeping the spirit of inquisitiveness alive in the study and outreach of astrophysics in St. Xavier's. Astrophysics have, in fact, always figured in the history of St. Xavier's, beginning with Father Eugene Lafont, who have traveled from Belgium in 1865 to participate in the educational front led by the Jesuits in Kolkata. He was one of the key figures in integrating science to the prevailing curriculum in our state. But he went way beyond the standard for establishing the first science laboratory and then the rooftop observatory and a meteorological unit. The meteorological unit came into headlines after predicting the killer storm of 1867 and saved hundreds of lives, although it could not save the photographic laboratory from blowing away in high winds. And in recent times, these high winds have also displaced the rooftop of sliding roof of our solar observatory on the roof. So the same high winds are there. The rooftop observatory hosted a giant 8-inch refractor telescope, and it unearthed significant findings in synchronization with leading European observatories. The observatory, however, fell into disuse and slept for a good 100 years before it was revived and reinstalled as dual observatories, standing on solid historic isolation piers with the inception of postgraduate studies in physics. Since then, it has been serving as a laboratory for PG students, a research platform for graduate students, and also as a part of the social outreach program for St. Xavier's. ZAS, the Xaverian Astronomical Society, was established in the previous year to extend the reach and ambit of astronomy to all sectors of the college and beyond to the grassroots level, piercing through the subject barriers and making it accessible to just about everyone, due largely to the efforts of Shashwat and Ankit, who had sold their hearts to the project. I believe that it is forging ahead steadily in that direction, and it is indeed very heartening to see that it has stood up to the causes and values that this college stands for in the time of the confining pandemic. This year, the speaker for the occasion is Dr. Shayan Basu, radio astronomer, whom I had the opportunity to know closely for several years, in which he had helped our PG and some UG students to pick up the basics of radio interferometry and hands-on experience with data analysis. Dr. Suparna Rai Chaudhuri, the only true astronomer in St. Xavier's, would of course introduce him more properly. I like him very much, and he is indeed a very resourceful person from which you, the students, can have your heart full. Shayan, I appreciate very much that you have agreed to speak to our students in this occasion. Thank you all very much for a pleasant hearing. I sincerely wish that Jazz finds its slice of heavens and takes everyone to, and of course back from the stars, and that too safely. And remember that safely is the keyword these days. Thank you again.
Thank you, sir, for your words. They were really enlightening. It seems now that the mood has been set for the webinar. However, before we get started, just a little housekeeping. Participants on the Zoom and on the YouTube platform will get time to ask questions to the speaker, but only after the whole webinar ends. So, I would request everyone present here to kindly turn off their audio and video so that there is no disturbance. If anyone wants to ask any question in the Zoom platform, they can type it out in the chat box, and the MC, after the webinar ends, will get back to them and they can ask the questions directly. For the YouTube viewers, they can type the questions in the live chat box, and our team will carry forward the question to the MC to be asked. Thank you. Now, I would invite Suparna Roy Chaudhuri, the Chief Mentor of XAIS, to introduce our guest speaker.
Thank you, Shagni. Can everybody hear me?
Yes, you're audible.
Respected Father Principal, respected dignitaries, esteemed faculty members are invited from ISRO, Dr. Debashish Chakraborty, the most important person of today's evening, our respected speaker, Dr. Shayan Basu, my dear students, ladies and gentlemen. A very good evening to everyone. It is indeed a great pleasure, Dr. Shibanji pointed out, to be introducing our speaker today, Dr. Shayan Basu. Dr. Shayan Basu is a researcher at the University of Pretoria. He is also affiliated to the Hartbeespock Radio Astronomy Observatory, Hartrau Betel, a research facility under the South African Radio Astronomy Observatory, SARAO. He has been also an integral part of the South African Large Telescope, which is better known as SALT, the largest optical telescope in the Southern Hemisphere. He completed his PhD in astronomy at the University of South Africa and is currently based at University of Pretoria. His main research interest ranges around mostly studying the structure of quasars using astrometric VLBI observations, which is basically very long baseline interferometry, which I'm sure he'll enlighten us about in his talk. And also, he has been lately taking interest in the Chandrayaan mission, so he would focus on in his talk, he has promised. He has also been an integral part of our growth in astrophysics and various college. He has been associated since 2015 with us, where, as Dr. Shivaji Banerjee pointed out, he actually taught the basic radio astronomy, us meaning our graduate students, and of course us also, and have also mentored some students with data and side us virtual observation experience, along with bringing to
Should I start or should we just wait for Supernadi to get back?
Sir, wait for a few minutes. There happens to be some network problem.
Okay.
Okay, sir.
hello, can you hear me?
Yes, ma'am. You're
Yeah. Sorry.
okay.
Sorry for the glitch. Hello.
Ma'am. Yes, ma'am. You're clearly audible now.
Okay. So as I was saying, he has been a very integral part of the growth of astrophysics in St. Xavier's College, and he has also brought on to the fore many other astronomers from around the world. One of them being Dr. Henry Throop, who has also been extremely generous in sharing his experiences of different NASA missions with us. So, Shayan, a very warm welcome to from all of us to you. It is really great to be seeing you again, and that you have agreed amongst your schedule to speak today evening. So, here's the stage for Shayan, Dr. Shayan Basu, for everyone.
Okay. First of all, I'd like to thank all of you guys in St. Xavier's College for conducting this beautiful event, and also let me give me a space to talk about all the research, all the exciting research that I've been doing. And first of all, I would like to thank Father Dr. Dominic Savio for a nice introduction, and then Dr. Sivaji Banerjee and Dr. Suparna Raichaudhuri for nice introduction, and Xavier's Astronomical Society. You guys are really doing a great job, and hopefully in the near future, I'll come and I'll visit you in person. So let's start the talk today. So today I'm going to talk about extragalactic radio sources for navigation. And this is also a part of my research that I have been doing since my PhD. And at present, I am the Sarao Research Fellow at Hartrau and also University of Pretoria. So navigation is all about going from one place to another. It can be in the space, it can be on the surface of the earth. So wherever we go, maybe we go by walking, we go somewhere by driving, and we also have some satellites, we have spacecrafts visiting other celestial bodies for some exciting science. For all these things, we need navigations. And to navigate through space, we need something with respect to which we can measure our speed, our positions, and everything. So here, this is a beautiful picture of our very own Milky Way galaxy. And we are at something very chaotic is happening at the center. We have a supermassive black hole, which is eating many stars. So something big is happening at the center, and we are very far away from the center. Perhaps our Milky Way galaxy is a spiral galaxy, which has like 4 arms, and our solar system is in between 2 arms, and we are almost at the outer position from the center. So we are at a safe location. But our solar system also making an orbit, and with a velocity of almost 828,000 kilometers per hour, as you can see, it takes almost 230 million years to make one complete orbit around the Milky Way galaxy. And our solar system so far made 5 complete orbits around the Milky Way galaxy. So that's about our position in a solar system of our Milky Way galaxy. So now, where we are, where is our planet in the space? That's something that we should know. And around our planet, we have hundreds of satellites orbiting our Earth. Some of them are communication satellites, some of them are for navigation satellites. So our space is almost full with all the satellites, and we also need to know where are these satellites. So that's also a part of navigation. And third one here is an example of New Horizon mission, with which Dr. Henry Throop was associated to, and he's still now busy with the mission. And most of you guys are not there in St. Xavier's when Henry came to visit St. Xavier's, and he gave a talk on the New Horizon mission, which is a flyby mission to Pluto. And this mission gives us very much new information about the Pluto. So that's an example of a spacecraft navigations in space. And as this kind of spacecrafts floats in the space, we also need to know where they are. In every seconds, every minute, we need to know their precise locations on the space so that we can also track them, and we are not going to lose any signal from all those spacecraft. So this is also an example of spacecraft navigations. And then let's come back to Earth on our surface. So on surface, top left corner, we need to know where we are. We most of us, we have smartphones, and we have GPS on our smartphones. And as soon as you turn on your GPS, you will know where you are. We also have GPS on our vehicles, and we need to know where we are going. And if our GPS fails, then something like the picture in the middle panel will happen to us. And then beneath our surface, we have tectonic plates. When everything started, there was a supercontinent, which we call it as a Gondwana land. And over the period of time, all these tectonic plates started to move away from each other, and thus they formed the 7 continents that we have at present. But all these tectonic plates are in constant motion. Some of them are moving away from each other, some of them are moving towards them. Suppose South Africa is moving towards India. Okay, so this is also happening beneath our surface, and it's also part of the navigation. So we need to know the rate of these tectonic plate movements every single year. So as you can see, like on the fourth picture, top corner, we have like almost 50 millimeter per year movement in our tectonic plate motions, and it seems to be very small, but it's pretty large. Okay, so we need to know all these things, and to track all these things, we need reference frames. So what are these reference frames? So reference frame is nothing but a collection of fixed point. It can be either on the ground or it can be on the sky as well. So reference frame with a fixed point on the ground, we call it terrestrial reference frames. And we also have a reference frame with fixed point on the sky. We call it celestial reference frames. And celestial reference frames, we have stars as a candidate. So when a reference frame is made of position of stars, we call it optical reference frame. And then we have extragalactic radio sources. So a reference frame which is made of the positions of extragalactic radio sources, we call it radio reference frame. And now stars as reference points. So when we go out at night, and if we look at the sky, night sky, then we'll see like stars appear to be as a fixed points on the sky. But in reality, they are not. They are in constant motions. Suppose if you look at a star today, and let's say 1 week after, if you can recognize the same star, then there is a higher possibility that you will see that star moved a bit from its original position. So we call it something as proper motion. So proper motion is an apparent angular motion of a celestial objects on the sky. So let's see a video clip from European Space Agency, in which you will see how stars move across the sky. So it's a nice view of our Milky Way galaxy. We have many nice dots. So these are all stars, and as you guys can see, they started to move. Okay, now they are moving, but remember, most of the stars, they are also a part of a constellation. like we have constellations like Cassiopeia. So now you can see all these stars in those constellations, they also move. Okay, like you can see Cassiopeia, Cepheus, Ursa Minor, Ursa Major. So all these stars within their very constellation, they also are in constant motion. And after a couple of years, all those constellations, they also move across the sky. So if we consider stars as a reference points on the sky, then it will be very difficult for us to keep track of all these applications that I showed you guys with the highest accuracy. So typically, the proper motion of stars is approximately 0.1 arc-second per year. But in the Barnard star, astronomers found that the largest proper motions recorded is like more than 10 arc-second per year, and it's a pretty big proper motion for a star. So that's why we don't use. So that's why stars are not very good choices for reference points. So now, extragalactic radio sources as reference points. So extragalactic radio sources selected for reference points, they are mainly quasars. So what are these quasars? I mean, the quasars are nothing but a subclass of active galactic nuclei, or AGN. And AGN, they are young galaxies with a supermassive black hole at the center. So now let's see an example of quasar, how it looks like, and how far they are.
Quasars are the most luminous objects in the universe. Now, astronomers using the European Southern Observatory have found a quasar that's more than 5 times more powerful than any previously seen. Astronomers on Earth first became aware that quasars existed in the 1950s. Back then, the term quasar meant quasi-stellar radio source because they looked like very bright points on the sky at radio frequencies. Now we've come to understand that they are actually gargantuan sprays of matter and energy powered by supermassive black holes in the centers of young galaxies. Wait, I hear you saying, don't black holes suck matter in? Well, sure they do, but as they do, they tend to shred that matter apart, spinning it up, forcing it outward at very high speeds. Researchers have cataloged more than 200,000 of these objects. The very nearest one is more than 600 million light years away from Earth, and most are at least 3 billion light years back in spacetime. But this discovery is the first to confirm the theorists' predictions that these cosmic blowtorches could truly be this hot and this bright. For Space.com, I'm Dave Brody.
So as you can see, guys, quasars are the brightest among the AGN, and then they are located at such a distance that they appear to be a fixed and point-like objects on the sky. So as they appear to be point-like on the sky, so it's much more easier to do all these navigations on the space or on the Earth with respect to all those fixed points on the sky. So now we need to have some instrument so that we can observe these radio sources. And for this purpose, we have radio telescopes. So radio telescopes are almost similar to a mobile phone that we carry. Like for mobile phones, all the mobile phones, they get the radio signals from the nearby tower. And for a radio telescope, it gets radio waves from the outer space, from all the galaxies. So in this picture, we have a radio telescope, which is observing in a wavelength, and radio waves from this galaxy is hitting the dish and then it reflects to a reflector, and then those waves are also coming to we call it control room, and there we do some computations, and then we create an image of those radio sources. And how good are these images? We have a term that we use, we call it angular resolution. So the highest angular resolution, the better we have angular resolution, the better we can see about these target sources. And angular resolution of a telescope is the smallest angle between close objects that can be seen clearly to be separate. And in this example, let's say we have a radio telescope of a diameter d. We are observing a radio source at a wavelength of lambda. So the angular resolution of our telescopes will be lambda over d. And its unit in radian. So, and you can see 1 radian is how many arc seconds. So now there is a table with instruments and how good they can see. So first, let's look at some optical instruments. So first is our very own eyes. So the diameter of our pupil, it's almost 3 to 4 millimeters during the day, but at night it also increased to 6 to 9 millimeter, because our pupil, it needs to low light situation. So that's why the diameter a bit increases at night. So with our eye, visible light, we have a resolution of 1 arc second. And then Hubble Space Telescope. We all see all these beautiful optical images of the galaxies for many years now. And Hubble Space Telescope is out there for almost 30 years now, sending us beautiful pictures. It's not only beautiful pictures, but it also discovers many beautiful phenomena. So the diameter of the Hubble Space Telescope is almost about 2.4 meter, and at visible light, it can observe at 0.04 arc second as well. So moving to radio. So here, from the example in the optical, like with human eye, we can see 1 arc minute. And then with Hubble Space Telescope, with a larger diameter, we move to arc second, okay? And with radio telescopes, if we keep increasing the diameter of the dishes, then we'll get better angular resolution. Means we can see much more detail about our target sources. So suppose we have a radio telescope with a diameter of 100 meter, that can give us like 7 arc minute at 21 centimeter wavelength. Then if we increase it to 300 meter, it can give us 4 arc minute, same wavelength. And then if we increase to 500 meter, it can give us 1 arc minute at 21 centimeter. So from this example, we can conclude to have a better resolution, we need to increase the diameter of the radio telescopes. So right now, okay, so this is an example of steerable radio telescope, which means you can just direct it to different angles. The entire dish can be moved to any angle that you want to observe. It's a green bank radio telescope. It's in USA, and it has a diameter of 100 meter, with which we can get almost 7 arc minute resolution at 21 centimeter. And then this is the largest single dish radio telescope that we have right now, and it's in China. It calls 500 meter aperture spherical telescope, or FAST. And as I showed you, with this kind of diameter, we can achieve almost to one arc minute of resolution at 21 centimeter wavelength. But there is a limit. You cannot just keep increasing the diameter of a steerable telescope as much as you want, because suppose you want to build a steerable radio telescope with 500 meter of diameter, you will not be able to do that. It's going to break. So for that one, radio astronomers came up with a good idea. Instead of building a very big radio telescope, they thought, okay, so let's use small telescopes and then connect all those small telescopes together to build a very big telescope which can have a maximum diameter which is equivalent to Earth's diameter, which is pretty large, which is almost 10,000 kilometers. And this is the technique that we call very long baseline interferometry, or VLBI. So in VLBI technique, what we do, as you can see, this is an example of the global VLBI array. And you can see all these telescopes. They are not located in one place, but they are located in different locations within a country or in different continents as well. So we use all these telescopes, and using all these small or medium size of telescopes, we create an virtual telescope which is almost equivalent to the diameter of our Earth. Okay, so that's what we call a VLBI technique. So this is an example of a VLBI array consisting of two radio dishes. Okay, they are separated by a distance b. They are observing a source at a wavelength of lambda. So for now, we have angular resolution which is lambda over b. So which is not anymore the diameter of the telescope, but it's the longest distance between two telescopes. So suppose you have a VLBI array with 5 radio telescopes. So B will be the longest distance between two telescopes in your 5 antenna array. So this is an example of the VLBA, which has 10 radio telescopes located in several locations in the United States. And this is an example of also the VLBI, but it has all the telescopes in one single place. And in the second case, we have the longest baseline, which is 25 kilometers. Okay, what happened? Okay, so the first one, as we can see, it called VLBA, and the second one is VLA. VLA is in New Mexico. And for the VLBA, we have the longest baseline of a length of 9,000 kilometers. And for the VLA, we have the baseline length of 25 kilometers. So let's observe a source at the same wavelength of 21 centimeter. So at 21 centimeter with a baseline length of 9,000 kilometers, we can achieve an angular resolution of almost 4 milliards seconds. And remember, with the largest single dish telescope FAST, with 500 meter diameter at the same wavelength, we can have angular resolution of 1 arc minute. So there you can see the clear difference between a single telescope and a VLBI. So with VLBI, we can achieve better resolution that can allow us to see many small details in a target source. So now, how good is VLBI? Okay, so let's take an example of Cygnus A. So it's a galaxy And with VLA at 6 centimeter wavelength, we can see there is a brightest dot at the center, and on the both side we have like blobs. If we zoom in with VLBI at the 6 centimeter, we can see what's this brightest point at the middle. And then we go down with lower wavelength. So as we can go down to lower wavelength, we can pick up some more structure of this source. So what's happening here? So we have a bright component at the center, okay? Then it emits a jet, okay? So all this reddish thing, they are the jet components. And as we keep increasing the wavelength, we can see much more detail. And with a millimeter wavelength, we can see that how this jet evolved, okay? So with increasing of wavelength, increasing in the sense we are going down, okay? So as we increase our wavelength, we can zoom into the source and we can pick up very small structure in the source. So that's why VLBI is much more important to pick up these very small scales in a target object. But again, with the VLBI technique, we can also measure the Earth size, its shape, its rotation, and its orientation in the space. And not only that, we also use the VLBI technique for GPS maps to measure the ocean tides, and then calibrate our clocks, and then also measure the tectonic plate movements, which can also give us some kind of idea with the earthquake. VLBI techniques can also be used to track tsunamis and also track the satellites with highest accuracy possible. So when we do all these things using VLBI, we call it VLBI technique in geodesy, okay? So let's see like how VLBI technique in geodesy works. So what's happening in the figure? We have two telescopes, which is also directed to a quasar, which is fixed point on the sky. Even though these telescopes are located in a different locations on the Earth, they are observing the quasar at the same time and at the same frequency. And they also have a baseline vector, which is B. Also, we have a unit vector S, which is towards the position of our source. And since these two radio telescopes are located in a different locations, the radio waves from the source will hit one station before another. So there we have a time lag, which is tau t. And to calculate the time delay, we just multiply the vector B with the unit vector S, and we divide it with the speed of light. And that's how you can get the time delay. And however, this time delay is very important to calculate the Earth orientation parameters. I'm pretty sure that most of you guys know that days are not actually 24 hours, okay? And geodetic VLBI gives us all these precise measurements about the Earth orientation parameters. However, in geodetic VLBI, once we measure the locations and distance between the sources, and we repeat all these measurements over, let's say, 10 years period of time, and using all these analyses, we can observe a very tiny and slow changes on the Earth's surface, like the continental drift that I showed you guys. It's almost at millimeter scales per year level. So radio astronomers by late 1960s, they proposed a catalog with the VLBI positions of quasars. And assuming that quasars are fixed point on the sky, and this radio catalog actually replaced the old FK5 optical catalog and was adopted by the International Astronomical Union in 1998. And the catalog is known as International Celestial Reference Frame. So the ICRF is a catalog with the VLBI positions of quasars, more than 4,000 quasars observed at 2.3 gigahertz, which is S band, and at 8.4 gigahertz, which is X band. So when in 1998, IAU adopted the first ICR catalog, there was only 608 quasars, and then they released in an extension of the ICRF1, which is called ICRF Extension 1, which had source positions of 667 quasars. And the recent one, which was adopted by the IAU in 2018. Now the ICRF3 has VLBI positions of more than 4,000 quasars. So as you guys can see, like with the every single ICRF, the number of sources have been increased using all these VLBI observations around the world. And not only that, with the increase of the source positions, we also increase the accuracy of the stability of the ICRF frame. However, to improve the accuracy of the frame, we need to have an equal distribution of the sources across the sky. And with an improvement of the accuracy of the sources in this frame, we can also improve the accuracy of the applications, including the navigation. And the axis stability of the ICRF3 is less than 10 micro arc second, so which is pretty stable. And there are some more details that all the geodetic VLBI observations that we use to maintain the accuracy of the ICRF, they are coordinated by the IVS. And the observations and the analysis from these geodetic VLBI observations, they contribute directly to the Space Geodesy project at NASA. So however, how does a geodetic VLBI session work? Okay. So for a geodetic VLBI session, we have 24 hours simultaneous 2.3 and 8.4 gigahertz of observations. And in these observations, we observe many quasars. Let's say for one example, the geodetic VLBI sessions that I use. So we observed mostly more than 30 quasars for this 24 hours period of time. And then we have stations in different continents. Let's say we have a station in South Africa, which is Hatrao. We have 4 or 5 stations in Australia. And let's say we also have a station in New Zealand. All these stations, they record the data of this 24-hour observation separately. And once the data recorded at each station, we e-shift all this data to one correlator center. So now we do it by e-shift, which is like transferring the data from one server to a central location. However, before we used to ship all this data to this correlator center. So this was like a courier sending to one place to another. So at the correlator center, all this data from different stations, they gets cross-correlated, and then we start our analysis. So this is the location of the telescopes in the IVS network. We have more than 45 telescopes sponsored by 40 organizations in 20 countries. And here all the black telescopes, they are the IVS site. And then the red ones are the future IVS site. And then the blue one, they are the operating VLBI site. So as you can see, HATRAO is the only VLBI operation stations in the African continent, which participates in global VLBI observations regularly. And at HATRAO, we have 2 radio telescopes so far. One is 26 meter in diameter and one is 15 meter in diameter. And then in Hobart, which is in Australia, they also have 2 radio telescopes. One is 26 meter and one is 12 meter. And in New Zealand also, they previously used to have only 1 telescope, which is 12 meter of diameter, but they converted a telecommunication dish for astronomical research purposes. So now they have 2 radio telescopes. The big one is 30 meter and the small one is 12 meter. So that's the 26 meter telescope at HATRAO. And this is the first NASA Deep Space Network stations in Southern Hemisphere. And with this very telescope, we also got the first image of the Mars. And as I mentioned before, HATRAO 26 meter telescope and 50 meter telescope, they both participate regularly in VLBI, global VLBI observations. However, in India, we don't have any telescope in the IVS network, but I am pretty confident that in the near future, we will have one from India. Because here you can see in Japan and Korea, they have many radio telescopes and they are operating and they are doing great sciences. But if we can have a telescope in India, then we can do better science with the VLBI technique. And if we have a telescope in India, then it will create a very nice network for Asian VLBI network. So I hope in the near future, we are gonna have one telescopes in India dedicated for geodetic VLBI observations. So now how a GPS works. So as we talk about the navigation, you have a smartphone, you have a GPS. So how does a GPS work? So GPS actually depends on a constellation of the satellite that are constantly broadcasting their locations and times to the GPS enabled devices such as our smartphone. And this is a picture of a satellite locations. So I was accidentally, and I was pretty much interested to see like how many satellites are there at any given time. So I did a nice research using this link, and you guys can also look at this link. And the number of satellites only for communication and navigation, I found it was 656. Okay, so our sky is pretty much populated with all these satellites for navigations and communications. So how a GPS works on your smartphone. So suppose you have a smartphone, as soon as you turn on your GPS location option, it will find 3 satellites which are close enough. Okay, so suppose your device will find a satellite 1, then it will look for the satellite 2, the nearby one, and then it will also look for a satellite 3. Okay, and the intersection where all these 3 circles meet, that's the position of your device. And that's how a GPS works on your smartphone. And all these satellites in the constellation, they also rely on the positions of the telescopes on the Earth and the Earth orientation parameter to rely their locations. So if we don't have accurate measurements of the EOPs and also the telescopes on the Earth, your GPS will not give you an accurate positions of your device. And for EOPs, we need geodetic VLBI observations. And that's why we need a fixed positions of a quasar, or let's say like thousands of quasars equally distributed on the sky to give us a better positions and better accurate EOPs and accurate positions of the telescope on the Earth. So let's now take an example of a spacecraft navigations. Okay, so this is an example of the spacecraft Juno, which is a NASA probe orbiting the planet Jupiter, which is pretty far from Earth, which is, as you can see, it's almost 639 million kilometers. So Juno was launched in August 2011, and as it launched, it did some maneuver. Okay, so it's still doing the deep space maneuver, September 2012. And as it will enter our orbit again, it will get some speed, and then it will have some slingshot, which by now I am pretty sure you know from our Mars orbital mission from ISRO. So that's how we also went to Mars, by using the slingshot. So it escaped from the Earth's gravity, and Jupiter is also now orbiting, and Juno is now approaching towards Jupiter. And as soon as it enters Jupiter's gravity, it started to orbit the planet. And it took Juno to arrive Jupiter almost 5 years time. But during this 5 years period of time, radio astronomers on the ground at the control center, they needed to know where is this spacecraft in every second or every minute. And for this purpose also, we use quasars for accurate tracking. So let's say we have a spacecraft, and we have two telescopes on the ground, which is now tracking the spacecraft. So we have a telescope 1, and then we have telescope 2. First, we will get signals from the spacecraft. Okay, so and it will be recorded in each station. Then we look for a quasar, which is also very nearby to the spacecraft, and for the quasar, we know the accurate position of the quasar. So first, we'll get the signal from the spacecraft, and then we'll observe the quasar, and then we'll cross-correlate two radio waves, one from the spacecraft and one from the quasar, and by cross-correlating, we will get the angular position of the spacecraft with respect to that quasar. So that's how we use quasars for accurate tracking of any spacecraft or any satellite. So that's how it works for accurate tracking of the satellite or spacecraft. So by now we know to have navigation with the highest accuracy, we need an equal distribution of the quasars on the sky. But for that one also, we need to have knowledge of quasar structure. How compact all these quasars, and how good we know about their accurate positions on the sky. And both of these are problems, okay? So to have an equal distribution of the quasars on the sky, that's the problem number 1. And quasar structure, it's not that easy to have quasar structure, and that's a problem too for us. So let's look at the problem one. So that's it. I'm pretty sure most of you guys know the recent SpaceX Crew Dragon that went to ISS with 2 astronauts and then they came back to Earth. So this is the trajectory map of that Crew Dragon satellite. So with the ICERA 3, if we plot the source distributions from the ICERA 3, then we will see there is a sudden drop of the number of sources below minus 30 degree of declination, which is southern hemisphere. So yes, we have increased the number of sources to 4,000 compared to 3,000 in ICERA 3, but still there is a disparity in the number of the sources between the northern hemisphere and the southern hemisphere. And this is the source distributions from ICERA 3. So green ones are from the ICERA 2, which has 3,414 quasar positions, and the yellow ones are ICERA 3, which has quasar positions of 4,536 quasars. So below minus 30 degree declination, we have less sources compared to the north. And below minus 45 degree, we have really serious problem. We don't have that many sources in the southern hemisphere. So to overcome this problem, we started to increase the number of sources in each geodetic VLBI sessions. But that's not only the solution. Besides the increase the number of the sources, we need to analyze the structure of these sources to which are fit as reference sources. So that's where the knowledge of quasar structure came, and that's where my research also contributes. So to understand the quasar structure, we needed a routine VLBI imaging program which didn't exist in the southern hemisphere before 2013 when I started my PhD. So I did routine imaging and quasar structure analysis at S and X band at multi-epoch. So on the left-hand side, that's how a quasar looked like. Okay, so it has a central black hole which has accretion disk, and then we also have a torus. And as all these interstellar medium, they fall into the black hole, it ejects relativistic plasma, which creates then a relativistic jet, and it also creates a shock, or we also call it as knots. So this is a telescope, and that's an accretion disk. This is a black hole. We have a torus, and depending on the line of sight, we look at a different angles of these jets. And that's an example, that's an actually pretty nice example of a galaxy, which is M87, means 87th celestial object in the Messier catalog. So the observing wavelength is millimeter wavelength, 7 millimeter. So when we have a viewing angle of 20 degree, we see this kind of structure. And as we increase our viewing angle, we can see the difference in the structure that our images also can pick. So now the very galaxy with the VLA at 6 centimeter wavelength, we see this is the core, and then we have all these jets are coming. So these are also knots. Even with the HST, we can also see the core, and all these are different components. And even with the X-ray Chandra telescope, we picked up all these like big bright component to the core. And what's happening here, once you start picking up all this kind of secondary components, it actually creates a superluminal motion on the sky for this source. And this kind of superluminal motion it also create an proper motion for this source. And if you have proper motions of a source, then that source will not be suitable for a reference frame use purposes. And then again, this is a source observed and imaged in 1997, and then imaged in 1998, and then imaged in 2008. And you can see how the second component from the core, it actually went through an evolution of a jet. Okay, so first it was pretty much adjacent to the core, and in the second epoch it started to move away from the core, and in the very third epoch you can see like two different components, one core, and then you can pick up a second component to the core. And if you select this kind of sources for your geodetic VLBI purposes, it's gonna give you pretty much big error in your EOP's calculations, which will eventually affect your navigation system. And that's why we need a multi-epoch imaging. So now quasar structure effect on geodetic VLBI. So we observe a source, and if we have a source with extended structure, all the telescopes will also start receiving the radio waves from the second component, as you can see here. And then the delay will have many components, like the geometric delay due to the location of the telescopes, then changing path length due to the Earth's rotation, then also delay due to the clocks. There will be clocks from the electronics. We have also delays from troposphere, ionosphere, and then we also have some effect from the special and general relativity. And then we'll have a contribution from the source structure. But it's also important how we observe a source. Like if we observe a source 90-degree orthogonal to a line of sight, then we are not going to see any structure. But as soon as we will start creating a viewing angle, we will start picking up all the extended structure if that source already has some structures. Okay, so in this example, the blue one, when we observe this source orthogonal to the baseline, we cannot see anything. And then the red ones are like the short baseline. But remember, with the VLBI, if you observe one source with the short baseline, then you will only see the large scale structure of the source, which for in this case, Hobart and Catherine both are located in Australia. So they create a short baseline. And when you observe this kind of source with short baseline, you will see the large scale structure. But as soon as you start increasing the baseline length, which is here the black arrow here, Hobart and Haftra, which is almost more than 5,000 kilometers apart from each other, you start picking up all these small details in the source. So that's why we need long baseline. And on the right hand side plot, you can see like as we increase the baseline length, we started to pick up the delay. Okay, and that's the main observables that we calculate in the geodetic VLBI, the delay due to the source structure. However, the source structure also can have effect on station position estimation. So as you can see, the no structure, then SI is structure index, which we use to measure the astrometric quality of any source. And if you have a structure index of 4, it means your source has extended structure and it will contribute to error in your station position estimations. And also the sources with extended structure, they are gonna affect your EOP's calculations as well. However, so what we can do to mitigate this kind of problem, we need to select quasars with point-like structure, accurately known positions, and will show no proper motions. And those are detectable on all the baselines in your VLBI network. So I have like 3 examples of the quasars. It's very good. It appears to be point-like. And then the second one, it has a little bit of structure, but still it's okay. But the third one is bad. Like if you have this kind of sources, then you are gonna have some extra delay in your calculations, and it's gonna eventually affect all the VLBI, geodetic VLBI observables, such as the EOPs and everything, and in turn they are gonna affect the navigation applications. So quasar structure analysis in Southern Hemisphere. So when I started in 2013, this was the scenario. We used to observe the sources, but we didn't have any kind of image of the sources. So we didn't know how a source looks like and how this source evolved with a period of time. And then I started my research, and this is the source looks like last year. So this is an image of the source from the last year. So even for this source, you can see an extended structure here. So that's why we need multi-epoch imaging of extragalactic radio sources to make our navigations better. So the VLBI, geodetic VLBI session that I use, it's almost like we have a minimum 4 radio dishes, 24-hour sessions, and it is known as Celestial Reference Frame Deep South, CRDS, conducted by the IVS, and principal investigator is Dr. Aled David, who was my PhD supervisor. And what we did, we used to increase the scan times so that we can get much information about the source. So if you increase a scan time from 1 minute to, let's say, 5 minutes, so 5 minutes scan time on source is going to give you much more information than 1 minute scan time. So that's why, since all these sources, they haven't been imaged before, so we started to increase the scan time to get much more information and to have a better imaging of the sources. They also mostly observe only ICRF sources, and they have like 5 or 6 observing sessions per year, which is pretty good for multi-epoch imaging, and also good for analyze the quasar structure at multi-epoch. So these are also 2 examples from my work, and we are actually writing a paper. So far I have completed multi-epoch VLBI imaging for more than 100 sources at 8.4 and 2.3 gigahertz. And for this source, when I did imaging for 2 epochs, which are separated by only 3 months, you can see like the source already started to show like the second component. Okay, so I need to do more imaging for this source just to make sure how it evolves. So the delay due to the structure, if a delay due to a structure is greater than 30 picoseconds, it's actually equivalent to 3 centimeter position error in your station position estimation. And it's gonna affect everything, including the calculation of the EOPs. So this is also time series analysis of a source structure position for a source, which is 0537 minus 441. And you can see this particular source shows some fluctuation in its positions over a period of time, which is like 8 years. So we are planning to analyze these sources for another, let's say, as many epochs as we can, just to understand its behavior and to get an idea whether these kind of sources can be used as a reference frame source or not. So to have an equal distribution of the CRF sources with accurately known positions and structure, it also helps us to do spacecraft navigation with the highest accuracy. And the recent ones I am gonna talk about is Chandrayaan-2, which happened last year. So Chandrayaan 2 was one of the most anticipated space missions after the MOM, Mars Orbital Mission. So Chandrayaan 2 was supposed to land, the Vikram lander was supposed to land on the moon's south pole. And then we used to, then there was a plan of having a program rover, which will just go around on the south pole and send us some uh, pretty new informations about the south pole of the moon. So that's the trajectory of the Chandrayaan 2. And for Chandrayaan 2, the ISRO used GSLV Mark III. So GSLV is because so for ISRO, we have GSLV and PSLV. So GSLV are the geosynchronous satellites which orbits the Earth around its geosynchronous orbit, and then the PSLV is used to orbit like this. So for Chandrayaan 2, ISRO used GSLV Mark III satellite, and it was launched on 22nd of July, if I'm not mistaken. And it was supposed to enter, and it actually entered moon's orbit on 20th of August. And then it was supposed to do the soft landing on 6th of September. So in this picture, you clearly see like how it happened. It was launched, and then it did earthbound maneuvers, and then after a couple of days, it got transferred to the LTT, Lunar Transfer Trajectory, and then it's like 0.9 when the lander orbiter separation happened, and 10 the landing on the moon's south pole. So why Chandrayaan 2 was so important to NASA? Actually, NASA is planning to send 2 astronauts on the south pole of the moon by 2024. Okay, so they are going to land on the moon, and the mission is almost for 10 days. And this is the time when NASA will send astronauts to the moon after Neil Armstrong. So it will be almost more than 50 years. Okay, and this is Artemis 1. So NASA is going to have Artemis 1, Artemis 2, and then when it will go to Artemis 3, which is like 2024, which is now like 4 years from now on. In Artemis 2020, in Artemis 3, the NASA is gonna send some astronauts who will land on the moon. And of course, it will also use the soft landing. And this is why NASA was pretty much interested to see Chandrayaan happening, because even with the Chandrayaan 2, we planned a soft landing on the south pole of the moon, so that NASA can get some kind of information like how to do soft landing on the moon. And this is the Artemis 1. You can read everything, all the trajectory and everything, how it's going to happen, and how it's going to return to Earth, and where it's going to land on the Earth. So it's gonna land on the Earth on Pacific Ocean. So as I mentioned, like Artemis 3 will do the manned landing. So which will be a remarkable thing to watch in our lifetime. So South Africa actually tracked the moon landing of Chandrayaan 2. So SANSA, which is a South African National Space Agency, ISRO contacted them to track the satellite. However, Hartrau 26-meter telescope was used for the tracking. So when you used to do all this kind of tracking, first of all, you will have some activity log. So it's a log with all the timings and stuff, what's happening like minute by minute. So we had the information like touchdown will be the 6th of September, and all these times are at UT. So it's 8:24:25 means it was almost 11:54 at night in Indian time. And then we set up that telescope so that it can also point out to the moon accurately. And once the landing started, we started to get some spectra from Vikram lander. Okay, so you see that spike, the blue spike. So that's the signal from the Vikram lander. It started to send us once it started to do the soft landing. So that's the picture from our control room on 6th of September night. So John, who is now busy, who was busy looking at the desktop, and the blue jacket was Peter Strompost, who is an engineer at Hartrau, and beside that, the gentleman from the SANSA, who also came down to Hartrau just to see everything is going smooth or not. But suddenly and unfortunately, we lost the signal. Okay, so that's what happened. We all know by now. It did a hard landing on the moon, and as per the news reports, and I don't want to go to much details, that the thrust of the Vikram lander was not actually working as we expected it to be working. So that's why it hit the moon surface very hard, and we lost the signal, and we couldn't do anything about it. But the good news is we are going to the moon again with Chandrayaan 3, which was supposed to happen in November or December 2020. But I'm not sure it's going to happen that soon, given the situation right now. But it's going to happen sometime next year. I don't know, but I don't want to talk about Chandrayaan 3 in detail. So the takeaway information from my talk is like radio telescopes are used to observe radio wave emitting sources, and quasars are the brightest in the AGN family. Located in huge distance, they appear to be fixed and point-like objects on the sky. For these characteristics, quasars are used to define and maintain the ICRF. And then ICRF source positions are used in different, various applications: sea level measurements, satellite tracking, spacecraft navigations, EOP calculations. However, at milliarc second scale, quasars exhibit source structure, and source structure can contribute error in accuracy for all these applications, including navigations. That's why we need multi-epoch VLBI imaging. And in Southern Hemisphere, we started a routine imaging program, and results and analysis from this program contributed significantly to the ICRF source selections. However, the research that I do, it will also contribute significantly to the science that the square kilometer array, which upon its completion will be the most sensitive and the biggest radio telescope in the world. So my research will also contribute to the SKA by providing a grid of reference sources in the Southern Hemisphere sky. And these are the people that I would like to acknowledge. And yeah, thank you. And stay safe. And now if you have any questions, then please ask me.
Thank you, sir. We move on now. We will select one question from Zoom, then we will move on to the YouTube questions. We have Shuman Pramanik over here. He has asked two questions in the chat box. I would request him to say one. Please unmute yourself and please turn on your video and ask the question.
Hello, can you hear me?
Yes, I can hear you. Yes.
Thank you for such a wonderful talk. So my question was, if the long base interferometry is the best way to get a good resolution image, then why people try to build larger detectors or larger telescopes like FAST? Because it needs uh, money to build those. So with those monies, they can build arrays. So is there any advantage?
Okay, so it's pretty good question. We actually need single dish radio telescopes as well. Okay,
Yeah. So
and single dish radio telescopes are pretty useful for pulsar. The pulsar tracking, to do pulsar observations and to get their positions and the sciences that they are also doing. And then we also used to have the single dish observations are actually essential to get the source flux densities on a daily basis. So which is why we need the big single dish telescopes to do the pulsar science, then supernova remnant science and everything. Remember, the VLBI only can give you the high angular resolution, okay?
okay.
But to do all these kind of sciences that I just mentioned, you need a big single dish telescopes, and which is why, even though we have two telescopes at Hatrao, which is 26 meter and 15 meter, we use 26 meter, the big one, for single dish observations every single day.
We also have Schwann telescope, Schwann array, and log periodic array. So those telescopes are also long base interferometry telescopes. So why they are not using in your work, or what is the difference of using them? Like
what did you say?
The Schwann array or the log periodic array.
Okay, so what are the frequencies that they use?
They are
I'm
long.
not.
They are low frequency arrays mainly. So
Okay, because I'm not sure about these
they are
two
lower than
telescopes.
GMRT, I think.
Sorry?
They are lower than GMRT, their operating frequency, I think. I'm not sure.
I would request Mr. Shuman Pramanik to restrict to one question since we need to get on with the schedule.
Okay, thank you.
Okay, thank
Okay.
you. Now we have one question from. Now we have two questions from you. Now we have two questions from you, which I will be reading out. One has been asked by Chandrima Kaur, how do quasars relate to black holes and why do they emit radio waves? Was the question audible?
Yeah, can you please just repeat the question one more time?
How do quasars relate to black holes and why do they emit radio waves?
Oh, okay. The first one, can you please repeat one more time? Because I don't know, I have some weak signals here.
So, were you able to understand the question?
Yes, I'm not just getting, because the internet from my side, it's a bit weak. So that's why.
Okay, so I'm repeating once again. How do quasars relate to black holes and why do they emit radio waves?
Okay, so first of all, at the center of every single galaxy, we have a supermassive black hole. Okay, so of course the quasars are being a part of the AGN family. They also have a supermassive black hole as well at the center. All right. So as I showed you the structure of the quasar, So with the jet, like if you go down to the base of the jet, you will find the position of the black hole. So however, I am not sure about whether you guys know that there was a fundamental physics prize in 2019, I think. There was a group who actually imaged a black hole in M87 galaxy. Sorry, can you hear me, guys?
Yes, sir. Please continue.
Yes, sir. Yes, sir.
Yeah. So actually, it is, there is a black hole in the quasar. So quasars are no different than any other AGN. So quasars are just the brightest among all the AGN, and they also host a supermassive black hole at the center. So does it answer your first question?
I believe it does answer the first question. We will move on to the next one, sir.
Yes.
The next one we have is from Mr. Satyajit Chakraborty. Do we use CCDs in radio telescopes? He asks.
No, we don't use CCDs on radio telescope because we don't count the photons. So we just receive the radio waves from the quasars or any extragalactic radio sources, and we actually collect the radio waves. So this is why we don't use CCDs on radio telescopes.
Thank you. Thank you. I think that's all for today for the questions. Since we had a load of questions, I would request Dr. Shayan Basu sir to share his details so that anybody who wanted to ask questions can contact him later. Now, we will take a short break to move on to our next part of the event. Yes, sir.
Anyone interested asking me questions, they can send me. Can I just post my email ID here?
Sure, sir. Sure, sir.
Yeah, can you see my email ID?
Sir, did you post it on the chat, sir?
Yes.
So it's not visible here. What we can do is you can send it to us and we would send it to all the participants, all the interested participants.
Okay, or you can also ask Supernadi for my email address. It's not a problem.
Yes, sir. Yes, sir. Of course. So now we would like to move on to the next part of our session. Some rules would be displayed on the screen while intermission is going on. Please keep them in mind. And I would request every attendee present here to turn on their videos so that we can take a screenshot. We will have the intermission for 2 minutes. Please wait kindly. Welcome back. Now we will proceed to the online students presentation, and I would request our moderators for this event, Navnil Sarangi and Shomaditya Halda, to take over. Thank you.
A very good evening to all and one present here today. Now we will be starting with the online students presentation. First, I would like to introduce myself. I am Navin Sarangi, the moderator for today, along with Shomodita Haldar, who will also be the moderator along with me. First, I would like to explicitly state out the rules of this online competition. The rules for the student speakers are so. Each student speaker will get 8 minutes to speak, followed by 2 minutes of question and answer session. After 7 minutes, a warning indication will be issued. If one exceeds the time limit, we would have to mute them. For the joint presentation to be delivered by 2 speakers simultaneously, they will get 16 minutes of speaking time, followed by 4 minutes of question and answer session. After 14 minutes, a warning indication will be issued. First, I would like to explicitly state out the rules of this online competition. The rules for the student speakers are so. Each student speaker will get 8 minutes. While asking the question, we would request the attendees to turn their videos on and introduce themselves before proceeding to the question. We would have to mute. For the joint presentation to be delivered by 2 speakers simultaneously, they will get 16 minutes of speaking time, followed by 4 minutes of question and answer session. After 14 minutes, a warning indication will be issued. First, I would like to state out the rules of this online competition. Now, I would like to invite Shuman Pramanik of IIT Kharagpur to kindly start his presentation and introduce themselves before proceeding to the questions. For the joint presentation simultaneously, it will get 16 minutes.
Is my screen is visible?
Yes, your screen is visible. Please continue.
Hello, everyone. I'm Shuman Pramanik from IIT Kharagpur. Today, I'm going to discuss about detection and theoretical aspects of very high energy gamma ray burst, or GRB. I have done this work under Dr. Debanjan Bose and Professor Reshmi Lakshmi from IIST Trivandrum. I would like to acknowledge them, and I would like to acknowledge the Xavier's Astronomical Society for this wonderful opportunity. Today, I'm going to discuss about discovery of gamma ray burst, then overview, then detectors and telescopes. Then I will be talking about a special GRB and a model of gamma ray burst. So how gamma ray burst discovered? It was an accidental discovery after the nuclear test ban treaty. So both United States and Soviet Union neither trusted each other. So fear from Soviet might try nuclear test perhaps at the far side of the moon. US launched a set of satellite system called Vela. Vela was equipped to detect high energy emission from nuclear burst. So on July 2nd, 1967, Vela detected a strange kind of burst unlike anything. This was the burst, this was the count versus time plot. We can see that that burst contained a peak following by a low energy after emission. Vela detected 16 such more bursts and ultimately tell that they are not coming from any known source or any man-made source. They are coming from deep space. So they named it as GRB or gamma ray burst. Okay, so gamma ray burst basically emission of very high energy gamma rays for very small time. So we can compare its total energy with the total energy of a star over its full lifetime. Let's say our sun over its full lifetime, that's around 10 billion years. The total energy can be comparable with the energy of a gamma ray burst for just few seconds. So this is very energetic, and we can say this is the most energetic electromagnetic source in the universe. Well, so on a 9 years mission of NASA's CGRO, that mission is called Burst and Transient Source Experiment. They plotted around 2,700 GRB locations all over the sky, and they plotted their positions. We can see in galactic coordinate, they are just homogeneously distributed, and there is no signature of presence of Milky Way galaxy or any other galaxy. So we can conclude that they are not coming from galactic source, rather they are coming from cosmological sources. From this video, we can see that they are just random in position and time, and there is no link between any two GRBs. They are just happening all over the sky. So depends on their lasting time, GRBs are divided into two classes. Short GRB last for less than 2 seconds, and long GRBs last for more than 2 seconds. The number of bursts versus their duration plot shows that there is two distinct populations of short burst and long burst. Less than 2 second population is short burst, more than 2 second population is long burst. So there must be some fundamental classification scheme, and that is their origin. Their very origin is different. Short burst mainly originated from mergers. We think they mainly originate from merger, to neutron star, or to compact star. When they merge, there is a huge energy release in terms of the gamma ray burst, and that is short gamma ray burst. The second kind mostly originated from supernova or kilonova emission or a dying star. So collapsing the star core takes some time, and that's why this kind of gamma ray burst are long duration gamma ray burst. Also, astronomers think that if a star fall on a black hole, then there is a certain energy increase of the black hole system, and there's that certain energy increase triggers to a burst in terms of the gamma ray burst. So whatever the source may be, we now know that the source is very energetic source. The end product is a black hole. So whenever we see a gamma ray burst from the sky, we can see a black hole being born there. Gamma ray bursts are the birth cries of a black hole. Now we know pulsar, we know that the mergers also radiate gravitational wave, and they radiate gamma ray burst also. So collaborative study of those two is the only way to examine the general relativity and Maxwell's electrodynamics in the strong environment. There is lots of physics involvement and lots of astrophysics involvement understanding the gamma ray burst. Now, can we see a gamma ray burst sitting on Earth? Actually, we can't, because our atmosphere, Earth atmosphere, is not allowing any gamma ray or high energy ray to fall on Earth. Atmosphere is only transparent to some visible light and to some X-ray. So gamma ray we can't see directly. So what we have to do is we have to build satellite telescopes, or rather we have to see them indirectly by Cherenkov emission. So there is two kinds of telescopes. These are the main satellite telescopes observing gamma ray burst, the NASA's CGRO, Compton Gamma Ray Observatory, Fermi, Integral, and Swift. So, and these are the most Cherenkov telescopes. They called Imaging Atmospheric Cherenkov Telescope. They are ground-based telescopes, and they see the gamma ray burst by Cherenkov emission. That's indirect detection. Well, so if one needs to understand gamma ray burst, one need to understand the light curve of a gamma ray burst. What is light curve? Is nothing but the number of photon or the rate of photon versus the time plot. And that light curve mainly contained a prompt emission, that is the main burst of gamma ray burst containing the most high energy emissions, followed by a after emission that is in low energy. So after emission can contain from low energy gamma ray up to radio wave. And most of the cases we only see after emission. We can't see prompt emission because it just pass out. So up to 2019, everything was fine. Lots of gamma ray GRBs have been detected, but no any GRB ever been detected with energy more than tera electron volt energy. Now on 14th January, there is a groundbreaking discovery by MAGIC telescope. They detected a GRB with tera electron volt energy. Now this detection, they plotted them and they got a well power law distribution. Power law means if we plot energy versus time, the energy, the flux follows power law in time. That is, flux is proportional to time to the power some exponent. That is the basically the slope of this. Well, so they got power law. So we now need new models to explain this kind of high energy emission. I have been working on a model, and in this talk there is no scope to explain that model in detail. I am just briefly telling what I have done is that if we solve expanding shell like structure, let's say GRB happens here and there is an expanding shell. If we just solve these three equations, the radius of the cell with time, the mass of the cell with radius, and the relativistic factor gamma with radius, what we get is radius is expanding, increasing with time, mass is increasing with radius, and the velocity is decreasing with mass. That is, velocity is decreasing with radius. Gamma is velocity. So I have plotted them, and what I got is that velocity, the gamma is velocity basically. Velocity is decreasing with time, radius is increasing with time, and with different adiabatic factors, there is different plot shows different adiabatic factor. What is adiabatic factor? That epsilon there. So if epsilon is 0, that is total no. So my time is up. Is that? Well, so
You have 1 minute left.
okay. So yeah, for different adiabatic factor, those plots are different. And also theta is a parameter. What is theta? Is the viewing angle, in which angle we are looking at the GRB. So for different theta also, I'm getting that velocity is decreasing with time and radius is increasing with time. Well, and if we plot the velocity, gamma is the basically velocity with radius, then that follows again a power law kind of distribution, that gamma is some r to the power the exponent, r to the power the slope. So to understanding the GRB system, we need this kind of models. Well, these are the reference I have been used for this talk. Thank you. And if you have any question or query, you can always mail me. You are welcome.
Okay. Thank you, Suman. Thank you, Suman, very much for your enchanting presentation.
Yeah,
okay.
Thank you.
So our next presenter is Anik Parvi from Presidency University. So Anik, you may share your screen and you can start your presentation. Anik?
Can you guys hear me? Okay, can you see my screen?
Yeah.
Okay. Hello, everyone. I'm Anik from Presidency University. So here I'm going to talk about the host dark matter halos of supermassive black hole. Now there are two types of black hole. One is called the stellar mass black hole, and the mass of this kind of black hole is roughly 8 to 15 solar mass. On the other hand, the mass of the supermassive black hole is 10 to the power 6 to 10 to the power 9 solar mass. So these supermassive black holes are really heavy. As we know, every massive galaxy has a supermassive black hole at their center, and some of them are active. Now, what do I mean by active? Active means this black hole accretes matter from their accretion disk and it grows big. In astrophysics, we call them the active galactic nuclei, or in short, the AGN. Okay, these AGNs release energy in the form of the jet. Okay, now you can see on the picture that the bright jet are coming from the central supermassive black hole. As these black holes accrete, they also release a huge amount of the energy to their neighboring environment, and a fraction of this energy gets coupled to its the surrounding gas, and this phenomena is known as the AGN feedback. Now, due to this feedback effect, there is an additional heat in the intracluster medium, and it is roughly to the 2 to 3 to the kiloelectron volt per particle. So each particle in the intercluster medium gets an extra heat, roughly 2 to 3 kiloelectron volt. Now, this is a famous image. This image is the observational proof that feedback is not just a textbook thing, it really exists in our universe. The huge red parts are the radio jets, which are coming from the central supermassive black hole, and the bluish region is the X-ray emission of the cluster, which is due to feedback. And now there are many other observational probes from which we can study this feedback effect, and one of the proposal is the Synapse-Zeldovich effect. Now, Synapse-Zeldovich effect arises due to inverse Compton scattering. In Compton scattering, a high energetic photon collides with the free electron. So the electron get energized and the energy of the photon decrease. In the inverse Compton scattering, the exact opposite thing happens. Here, the CMB photon get scattered by the high energetic electrons and high energetic electrons in the galaxy cluster. Okay. The energy of the CMB photon is 10 to the power of the -4 electron volt roughly, and these photons follow the black body distribution. On the other hand, the energy of the electrons in the galaxy cluster are in the order of the kilo-electron volt. So we can consider these electrons as the non-relativistic particles because their kinetic energy is much less than their rest mass energy, which is in the order of giga-electron volt. And also these electrons follow the Maxwell-Boltzmann distribution. So the CMB photons collides with another electron with any random energy in the energy range. That's why the spectrum gets distorted. Okay, in the graph, the right one, the solid line indicates the actual CMB spectrum, and the dotted line indicates the distorted spectrum. So you can see there's a spectral shift between them, between this two original spectrum and the distorted spectrum. And this shift is because the collision of the CMB photon and the electron. Okay, this is actually the working formula. Here, the dN is the co-moving density, and this dV is the co-moving volume, and the capital N as a function of m is the mean occupation function. I will not dive into the details and all this stuff, but let's just remember that the y parameter is corresponds to the SZ signal. Now, this graph has a great importance, and these 3 points, the points in the box, actually the pink and orange one, are actually the experimental points, and all the other points are the theoretical ones. And you can see at high redshift there is an enhancement of SZ signal, which is coming from the feedback. But in a low redshift, it is not sure whether the signal is coming from the feedback or it is from the gas in the intracluster medium. So my work lies here. I check how much this y parameter changes at the low redshift, and I found that the change is very much negligible. Okay, I will skip all the details because it's very much hazy and messy, the model thing. And okay, so if anyone is interested about the model and how I get this working formula, so they can contact me. Here's my reference, and thank you.
Thank you so much. Okay. If anyone has a question from the Zoom account, I would kindly request them to unmute themselves and ask first Shumon Pramanik. Do we have any questions for Shumon Pramanik from the Zoom account? Okay. We have a question for Shumon Pramanik from YouTube. Can GBR be considered as a hypothetical concept called white hole? Shumon, if you can unmute yourself and answer the question, please.
Yeah, it's not basically because GRBs are the originated from black holes, and the concept of white hole is something different that is opposite of black hole, I think. So it's not.
Thank you for your answer, Shumon. I would kindly request you to mute yourself. Is there any question from the Zoom account for Mr. Onik Parui? If there is no question for him, we will move on to our next speaker, which is Ms. Ankita De and Anushi Sen. They will be co-hosting together. I'll kindly request them to start sharing their presentation. Can you please start sharing a presentation, please? Your time has already started. Please start your presentation.
There is a network problem. I'm not finding my partner.
Okay. We will wait for 2 minutes while I have another question for Mr. Onik Parui.
Thank you.
Mr. Onik Parui, if you could kindly unmute yourself and answer this question. What are the effects of SNE1A progenitors on galactic chemical evolution? Mr. Onik Parui, if you could please unmute yourself and answer this question. Mr. Onik Parui? Okay, it seems that we... Okay, please wait.
Yes, can you please repeat the question, please?
Yes, sure. What are the effects of SNE1A progenitors on galactic chemical evolution?
Actually, I don't know about the SN1 progenitors.
Okay, thank you for your answer. We'll take that into consideration. Mr. Onik Parui, we have one more question for you. Is there any danger of a closed GRB to Earth?
It's, I think, my question.
I don't work with the GRB.
I'm really sorry. This question is for Shumon Pramanik. What is the danger of a closed GRB to the Earth?
Yes, it's dangerous, and it's may cause of mass extinction because it's huge energetic, and if one happens very near to us, and as we know that GRB are pointed, so they are kind laser kind of. So if they point it on Earth, then it will be harmful, very much harmful.
Thank you for your answer. Ms. Ankita De and Ms. Anushi Sen, are you ready with your presentation?
Yes, we are ready.
Please start presenting.
Firstly, we'd like to thank all the organizing members and our audience giving us this opportunity, and we'll start our presentation.
I would request you to, if possible, kindly switch on your videos also.
Today, myself, Ankita De from Native Ribbon College, and my friend Anusri Sen from St. Xavier's College are going to convey a presentation on the topic electron-acoustic solitary waves in a Fermi-plasma and quantum degenerate plasma. Would like to acknowledge our supervisors, Dr. Sarnik Chandra, and our project partners. Here's the content of our talk. Firstly, we'll discuss what is plasma, then plasma in astrophysics, then exciting phenomena in astrophysics, and physics behind plasma, classification of plasma, study of non-linear and non-linear behavior, and what is shock, and conclusion, and then further aspects of plasma in astrophysics. At first, we come to our first topic, what is plasma? Plasma is considered as the fourth state of matter, which is first introduced by Langmuir in 1920. As we know, solid is heated, it becomes liquid. On further heating, liquid becomes gas. If we heat gaseous atoms to some extent of temperature around 11,000 Kelvin or at low density, as we can see in this picture, the electron in atom will be stripped free and leaving positively charged nucleus forms an ion. Thus, plasma is formed. Now we'll see there are so many astrophysical evidences where we can find plasma. The vast majority of the volume of the visible universe is thought to consist of plasma. As we can see, in stars, cosmic plasma emits light, as can be seen by gazing at the night sky. Also, we can find plasma in sun and solar wind, in compact stars like white dwarf neutron stars, and interstellar medium, which is space between star systems, and intergalactic medium, which is space between galaxies, and atmosphere of some hot planets, and accretion disk of black hole, as here we can see, and I-Jupiter flux 2, and interstellar nebula. This is the corresponding picture, and active galactic nuclei. Now the question is, do we can see plasma in terrestrial light? The answer is yes, we can. In aurora, northern hemisphere, it is called aurora borealis, and in southern hemisphere, it is known as aurora australis. Secondly, in the polar wind and plasma fountain, here we can see sun emits continuous stream of energetic charged particles, that is solar wind. Auroras are the result of disturbances in the Earth's magnetosphere caused by solar wind. In this picture, we can see the continuous stream coming from the sun carried out into the space along magnetic field lines and interact with the gaseous particles in the Earth's upper magnetosphere. The resulting ionization, we can see, it will emit light of varying color in the polar region. That is aurora. But luckily, Earth is shielded by magnetic field, its own magnetosphere. So the energetic charged particles, most of the energetic charged particles get deflected and we are safe. And lightning is another example of plasma present at Earth's surface. It's due to charge breakdown from cloud to Earth's surface. And other examples are blue jets, blue starters, and neon lights. Now we are going to state physics behind plasma. First, it's quasi-neutrality, describe apparent charge neutrality. And second is collective behavior and Debye shaping. This is the expression for Debye, the distance over which quasi-neutrality may break down. Criteria for plasma are stated here. Plasma frequency greater than 1, wave Debye length very less than plasma parameter, and number of ions inside Debye sphere very greater than 1. Further, we'll come across the classification of acoustic waves in plasma system depending upon the main vibrating element. They are electrostatic, ion acoustic, electrostatic, and dusty. Depending upon pressure loss, we can classify plasma system as classical, quantum ultra-relativistic, quantum sub-relativistic, and Fermi. Here we are dealing with last two topics. Here we study the analytical part of plasma, both linear and nonlinear behavior using different techniques. To study the analytical part, we have done the normalization so that our calculation get independent of dimensions and units. These are normalized governing equation for quantum plasma, and these are for Fermi plasma. Is corresponding continuity equation and momentum equations and Poisson's equation, and this for similar for Fermi plasma. Here we come to the discussion of dispersion relation, which given the relationship between frequency and wave number. Now we study linear behavior of electrostatic mode of quantum plasma consisting non-inertial degenerate electrons and ions under degeneracy pressure, which arises due to implication of Pauli's exclusion principle. Quantum plasma are important inside white dwarf and neutron star. Using perturbation relation, we can find this dispersion relation, which is a relationship between frequency and wave number, taking wave number as complex quantity, which is k1 plus ik2. These three are graphical representation. This is real dispersion curve for different values of quantum parameter. These are imaginary dispersion relation curve for different values of quantum parameter, and this dispersion curve is for different values of viscosity of ions. Now we'll come to the linear dispersion relationship of our electron acoustic solitary wave in Fermi plasma, which consists of non-interacting fermions, hot and cold electrons and ions under Fermi pressure. Fermi plasmas are important inside neutron star system and lab-made plasmas. When plasma density is sufficiently high so that the average interparticle distances becomes of the order of de Broglie's wavelength of electron, the quantum mechanical effect can be ignored here. And if temperature is lower than electron Fermi temperature, the energy of the system is given by Fermi energy. Using the perturbation expansion as stated here, we can find the dispersion relation here. And it's a dispersion relation between frequency and complex wave number. These three are corresponding graphical representation. First, this first curve represents dispersion curve for different values of quantum parameters. Second one is for different values of viscosity of cold electrons, and third one is for different values of thermal velocity. Now we'll proceed to the next slide, which will describe by my partner Anushree Sen.
Hello. I think I am audible.
Yes, you are audible. Yeah, you are.
Nextly, we are going to study the nonlinear behavior in. It's not working. Okay. Nextly, we are going to discuss the nonlinear behavior in quantum degenerate plasma and the Fermi plasma, deriving the Kedvy-Burgess equations using the standard reductive perturbation techniques as followed in the slide you can see here. So we are getting the Kedvy-Burgess equations like this form, and this is same for both quantum plasma as well as Fermi plasma, but the constant values for ND are a difference. Using further calculations, that is using tan hyperbolic method and introducing a new variable psi equal to zeta minus beta, we are getting the final solution like this for quantum plasma, and in the next slide we are getting this kind of solutions for Kedvy-Burgess equations in the same way. Now, these solutions is used to study the formation and behavior of shock waves. To analyze solitary and shock profiles, we first need to know what is soliton. Now, soliton is a quantum or quasi-particle propagating at a as a traveling non-dissipative wave, which maintain its shape when traveling at a constant speed, irrespective of any other disturbances. Now here we are going to study the solitary and shock behavior as well. The solitary behavior, here the orange and blue curve shows the solitary behavior, that is the symmetry in the curve, whereas this green curve shows the shock profile, that is the asymmetry in the curve. Here we can see the plot of phi versus xi, that is the space coordinate for different values of viscosity. With the increase in viscosity, the solitary behavior gets diminished and the shock profile gets prominent. In the second plot, we can see the dependence of phi upon the space coordinate for different values of h. This is solitary indeed. In the third graph, there is a contrary behavior with the increasing value of v0, that is the phase transitional velocity. There is an increase in its solitary behavior with the increase in value of v0, and the corresponding 3D plots are given here. In the similar way, we have plotted for Fermi plasma as well for different values of h and eta naught in the similar manner. Now coming to the point, that is what is shock. In physics, a shock wave, also called a shock, is a type of propagating disturbances that moves faster than the local speed of sound in the medium, that is root over gamma p by rho. Like an ordinary wave, a shock wave carries energy and it can also propagate through a medium, but it is characterized by the abrupt discontinuous change in its pressure, temperature, and density of the medium. Now we can ask that how does the shock differ from solitons? Unlike solitons, the energy and the speed of the shock waves alone dissipate relatively quickly with the distance. This is the difference, okay? Now when a shock wave passes through a matter, then the energy is preserved, but the entropy increases. Therefore, we should always remember that shock waves are strongly irreversible process, right? Now, shock waves generally results from the collisions of two flows of interaction due to interaction between the small scale flows and the large scale flows as well. And they are found in active galactic nuclei jets, in galaxy clusters, etc. So here we are coming to a neutron star. That is a star which is having a very small radius and a very high density. So we can say that the surface of a neutron star can be thought of consisting of Fermi plasma as well, right? Now, if we consider a system of particles, they are approaching towards the neutron star with a velocity. So their velocity gradually increases. But when they fall into the neutron star, they have the maximum velocity. But at the very instant of time, when they touch the neutron surface, then their velocity becomes zero. So there is a change, abrupt change in its velocity distribution. This can be said to be a shock. We can say again that with the further accumulation in a large number on the surface of this neutron star, there will be a huge change in its pressure, in its temperature as well. So there is a shock again. Now, depending upon whether the shock is invariant under time, we can say it is stationary shock or unstationary shock. And when they are getting, accumulated on the surface, they will form ripples and we will get a bi-Gaussian structure. And therefore, we can classify them as moving shocks as well. There can be standing shocks also because the radius of the neutron star is constant here. So in the next slide, you can see another neutron star as well. Now we are going to discuss this kind of shock phenomena with this graph. As you can see here, we have plotted the energy with the normalized distance using some simulation method. You can see how the shocks are getting, created, and after that, how the amplitude and the width are changing. Again, this has got diminished. Then again, the shocks are getting formed. Right? I think this is clear from this video clip. So next, we are coming to the conclusion. That is, stability of solitons and formation of shock waves is strongly dependent on the velocity distribution of ions. It is again evident that for larger dissipation of shock becomes more prominent and the profile becomes steeper. If we include some higher order correction terms or any other species of particles like positrons, electrons, ion beams, then this will make our astrophysical plasma study much realistic, but it will be hard to deal with this kind of nonlinear equations analytically as well. So what we can do in further work, we can study the inner structure of neutron stars, including magnetic field. We can introduce higher order perturbations. We can study rogue waves, that is high energetic, large amplitude waves. They will say whether the waves are stable or not. We can study forced KdV solution, introducing the external some force using HAM, homotopy analytical method simulation, and there are further works also. So we can conclude our presentation here with the references and with the question whether we can see a shock inside a sun, for higher density. The answer will be no, because the radius of the sun is much higher than the distance between the shock and the sun center. So the dynamics of the particle will be governed by the dynamics of the sun, and we cannot find any shock inside the sun. So here we end our brief presentation. Hope you have enjoyed. So thanking you.
Okay. Thank you, Ankita and Anusri, so much for your enchanting presentation. Now, we would like to ask our Zoom attendees if they have any questions. So, is there anyone who want to ask any questions to Ankita and Anusri?
Yeah, I have a question.
So, you can start, open your video and you can ask a question.
Is it okay if I don't open the video? Actually, I have some problems with my video. Can I
Okay, then
directly
carry on.
ask the question?
Yeah,
Okay,
you
thank
may
you.
carry on.
Okay, so that was a brilliant video session, like a brilliant PPT. My question is, you mentioned about your study of the quantum hydrodynamic model and the KDVB equation. So basically my question is, can you explain about kappa distribution and its role in magnetospheric and astrophysical environments? Or basically, how did you correlate QHM and KDVB?
Hello? Hello?
You are audible. Please continue.
Okay, so thank you for your question. So basically, we consider different kind of distribution. Like we can consider kappa distribution, Maxwellian distribution, depending upon under which condition we are working with, right? And you have asked that how we can relate quantum hydrodynamic model with our Kervy-Burgess equation. So when the density is much higher, then we have to consider the quantum degeneracy pressure as well. Therefore, we are considering quantum hydrodynamic model to study our Kervy-Burgess equation. Now, this Kervy-Burgess equation is something which is telling us nonlinear behavior. So, and including this Burgess term, we are saying something which is displaced from its equilibrium value as well. Okay, so in quantum hydrodynamic model, we should introduce some instabilities or fluctuations from equilibrium position as well. Therefore, we can relate quantum hydrodynamic model with Kervy-Burgess equations also. So thank you.
Okay, thank you, Anusri, so much. Is there any other question? So I guess there are no other questions. So we can call our next speaker, student speaker. The next student speaker is Vinvaram Jat from IIT Dhanbad. So Vinvaram, you can share your screen and start your presentation.
Yeah, thank you. So first of all, I would like to thank you all, and I hope you are doing well in these quarantine days. So my presentation is about black hole. So if you are an astronomical enthusiast, you must have had a question about black hole. I cannot scroll it. Just a second. Hello, can you guys see my screen?
Please continue.
So you must have had a question that what if someone approaches the black hole? So it's a black hole. Suppose that I'm not going to black hole. I know what happens if I go to black hole. So I'll send my friend right towards the black hole, right towards the singularity of the black hole. So it's the photon sphere, and this boundary over here is called event horizon. So we know that the flat space matrix in Euclidean geometry is looks like this. So we also know that in a black hole, there's large gravitational force pulling us towards it. So the space-time bends, it curves. So for curved space-time, Schwarzschild came with a solution. This equation looks like this. So we can set C equals to 0. It's just a matter of units that we are using. So if we set C equals to 0, we get this equation over here. So next, what we will do is we will calculate Xn integral. The Xn integral, through Xn integral, we can calculate the Lagrangian. Now, we can say that the particle or the friend that I'm sending towards the black hole will move in geodesic. So what's a geodesic? It's the shortest distance between 2 points that we are going through. So in Euclidean geometry, we can say that it's a straight line. So in classical mechanics, action is governed by this equation. Action is given by this equation over here. L over here is Lagrangian, but the relativistic action over here is looks like this. So here we know that the Lagrangian is energy, is in units of energy. So it's energy and the tau square. This is called proper interval, proper time. So this is in the units of time, and this is in the units of energy. So overall, we get the relativistic action like this. So again, we will set C equals to 0, and we will get the action equation like this. So we know that the particle that we are sending, the friend that we are sending, is not traveling angularly towards the black hole. It is going right towards the center of the black hole, right towards the singularity. So the action will look like this. We will, set d theta and d phi equals to 0. There will be no change in angles. Okay, so the action will look like this. Now, if we compare the relativistic action equation over here with the equation we have in classical mechanics, the conventional action equation, which looks like this. The font that are in black will represent Lagrangian, which comes out to be this equation. So over here, r dot is the velocity. dr by dt to the whole square is the velocity. So energy, we know that is conserved. Energy is always conserved along during this motion. So energy is equal to Hamiltonian. We know that, right? So Hamiltonian is given by P q dot minus L, Lagrangian. P over here is generalized momentum, and q dot is the velocity itself. So by solving this equation and putting all the values in this equation, we get Hamiltonian like this. This is the energy of the particle which is approaching the black hole. So what we get, we will rearrange the equation. We will rearrange this equation, and we will get velocity in terms of energy and the distance. This is the distance from the singularity, from the center of the black hole. So this is the equation that we get. This is velocity and this is energy. So what happens when r equals to 2 mg? And when we put this value of r over here, we can see that this term as well as this term vanishes. They both goes to 0. So at r equals, we know that c square equals to 1. It's all the matter of units that we are using. So r equals to 2 mg over c square. At this value of radius, the distance from center of the black hole, we can say that the velocity goes to 0. So this value of r is called Schwarzschild radius, and the boundary is called the event horizon of the black hole. So what is the conclusion of this talk? We can now say that we can never see him going inside the black hole. So what do I mean by that? We can, I started with this schematic. So here is my friend. He will go towards the black hole in a straight line. So he will cross the black hole photon pair and then arrives here. He will reduce its velocity. First, its velocity will increase. We can tell that by this equation. Then this its velocity starts to decrease gradually, and at this point, right at this point, just before the event horizon, we can say that its velocity goes to 0. According to me, its velocity goes to 0. So we can say that we can never see him falling into the black hole. Obviously, we talk about black holes squeezing and the mass and tidal forces and all that. We can never see him again. But what we actually see is that someone can never get into the black hole from our perspective. So that's all that's all about my presentation. I hope you understood it. I hope you enjoyed it. I hope you got the answer of your question. Thank you. Thanks a lot. That's it.
Thank you, Bhinwaram. That we will request the Zoom account holders to ask any question, should they have any. Is there any question for him? If there's no question for him, then we'll move on to a question we have from YouTube. My question is that when we are finding the Hamiltonian, why we are not finding it directly by using the generalized co-coordinates. Rather, we are first finding the action integral, then Lagrangian, and then Hamiltonian. If you can please answer this question.
It's all the matter of simplicity. How easily can you find those equations which are governing? So here we can see that after finding the Lagrangian, we can also put these values in Euler-Lagrangian equation, and straightforwardly we can find the equations of motion by that equation, Euler-Lagrangian equation. So it's all the matter of simplicity. How easily can we find our answer that we are looking for? So it's just a matter of that. That's it. We can find it in many ways. We can do anything what we want in Minkowski space with right equations, right? So it's all about it. Thank you.
This question was from Ritvik Ghoshal. Is there any more question for him? Well, thank you very much for your presentation.
Yeah, thank you.
Thank you to all the participants. And I would also like to thank Navnil and Shomaditya for handling so well. Since we've reached the end note, I would kindly like to point out to our YouTube viewers that a feedback link has been uploaded in the comment section. So please fill it up so that we can get your feedback, and also it'd be easier for us to send you e-certificates. Now, as a postlude to today's event, I would request Dr. Indranath Chaudhary, Head of the Physics Department of St. Xavier's College, Kolkata, to deliver the vote of thanks.
A very good evening. Respected dignitaries, professors, my dear students, and all present in today's webinar. It's my pleasant duty to propose the vote of thanks for this wonderful event organized by the Department of Physics, St. Xavier's College, Autonomous, Kolkata, in collaboration with the Xaverian Astronomical Society, XAS. I would like to take this opportunity to thank all whose untiring efforts and determination has made this event a grand success. I would like to express my sincere gratitude to respected Father Principal Dr. Dominic Savio SJ, respected Vice Principal Professor Bertram Da Silva, respected Deans Professor Tapati Dotto and Professor Orgho Banerjee for their constant encouragement and advice. I am grateful to Dr. Oyon Chandra, Member Secretary, Academic Council, Dr. Arup Kumar Mitro, Associate Controller of Exam, Dr. Partha Pratim Ghosh, the IQAC Coordinator, Professor Romit Beed and Professor Joyati Ghosh Dostidar from the Computer Science Department for supporting this event in different ways. In a special way, I must mention our deep sense of appreciation for our guest speaker, Dr. Shayan Bosu, for delivering such a gripping talk. We are really inspired by your great exposition on this subject. Thank you, Dr. Bosu. I would like to express my sincere gratitude to my dear colleagues from Physics Department, Dr. Shivaji Banerjee, the Deputy President of XAS, Dr. Suparna Rai Chaudhary, Chief Mentor of XAS and the coordinator of this event, Dr. Tanaya Bhattacharya and Dr. Sharburi Guho for being there as advisors and mentors and guiding the students for the presenting this talk, their talk. Without your active participation, this event would not be possible. I would like to thank in a special way all the student speakers for sharing their talents in astronomy. It is my privilege and I am very glad to thank our beloved students, Mr. Shashwat Sharaf, the secretary, and Ankit Kumar Gupta, the assistant secretary, and the rest of the core committee of XAS for taking this initiative and organizing such a wonderful event in this unprecedented condition. Looking forward to more such activities in future. I am also like to thank Mr. Bappaditya Manna, Mr. Shubhendu Chatterjee, and Mr. Srijan Sen for their assistance to handle the online platform. Finally, I would like to take this opportunity to place on record our hearty thanks to each and every faculty member and the student present here today. And last but not the least, our audience members on Zoom as well as on YouTube. Everyone who tuned in today to watch the event and to be a part of it. I am sorry if I miss someone unintentionally. We are truly thankful to each and every one of who has been with us in spirit and in person. Thank you so much.
Thank you, sir, for delivering such a wonderful vote of thanks. I would like to thank you from behalf of XAS for your active participation and for making this event a success. Now,
Thank you.
we have come to the end of the event. Before we conclude, I would like to inform our Zoom attendees that a feedback form has been uploaded in the chat box. Please take your time to fill it up. Since all good things must come to an end, so have we reached the end of this wonderful event. We would like to surely see you all in more future events. We wish you that you will stay safe in this pandemic situation and that we will surely rise above the pandemic. Thank you.